I'm one of the people who's been here besides Zane at pretty much every school. I think I missed one or two along the way. I don't remember for sure, but from the beginning. So it's always fun to be back. It's always memorable and really important part of my life. So it's good to be here every year, except for the allergies part. So okay, so what I want to do is Dan was saying we're going to tag team on giving you some very rapid fire background on programming language theory, because the way we designed our lectures is basically to set you up with the basics that you need for each of the other lecturers who are going into more technical detail on some particular topic. Okay, so that's the plan. Okay, so each day Dan and I this week will be swapping back and forth, and so that's the idea. Okay, as far as questions, feel free to interrupt, ask questions. My hearing is poor. It would be helpful if someone would relay the questions to the front, because even with a hearing aid, I often can't hear or make out what the question is. So please indulge me on that. I can't do anything about it, so we'll manage. If the questions become more open-ended and discursive, we have an afternoon session in which we can have more extensive discussions or breakout sessions or anything like that. So at some point I might just say, let's leave that for later or something like that, okay? And then because of the disparate backgrounds of people, don't feel uncomfortable if you think that like, oh my God, this is going too fast, and also be indulgent and try to get something out of it if you feel like, oh, I know all this stuff, I've seen it before, because maybe there's some twists in there that you haven't seen before, so I hope you'll get something out of it in any case. Okay, so that's the plan. Okay, so the thing that I want to address today by example is what does it mean for a programming language to exist? Might as well start with that. Okay, after all, if we're going to be talking about programming languages, then it's only fair to try to specify what did we even mean by a programming language. So this is the first thing. So today what I want to do is illustrate sort of definitional methodology for programming languages. More and more often, this kind of tools become useful, and people commonly use them. In the course of my career, it went from alien, bizarro guy from Mars to like more or less common sense. So I'm going to sort of give you the summary of that view. And so what I want to do is I want to start out by saying, well, a programming language consists of two major parts in the way we're going to talk about it. Okay, and that's the thing what we're going to do, that we're going to define. So how do we define a programming language? And we're going to do two things. One is a statics, which I'll call the statics, which is sort of what are the programs, just in some sense syntactically, how are you going to write them down, and the dynamics, which is how do we run them. So, and this is what we need to specify. Okay, and the idea is we'll give both of these things. So this, in some sense, there's sometimes in older literature especially, or I've seen other people get confused about what constitutes the language. In some sense, the statics, by very informal, ordinary uses of words, could call that the language because it's just the thing that you write down. But I would say that it's not. I mean, there's no point in doing that if you don't have a dynamics, if you don't know how to run programs. So really the kind of two things go together. But sometimes you'll see people calling that the language, and so we have to do that. Okay, so that's the sort of general setup. And then what is going to happen is that we are going to ensure, so then a very basic criterion is that these should be coherent in some way. Okay, so there's a kind of, let's call it coherence. Okay, so there's a basic criterion called coherence, which we're going to need, that tells you the statics and the dynamics fit together. So that's just the basic criterion to say you've managed to say something meaningful that we should bother to listen to you. If it's not coherent, then the whole thing doesn't make a hell of a lot of sense. Okay, so that's the sort of setup. So that's what we're going to do. And this morning, I'm going to very rapidly go through all of these things. Okay, so the first thing is what is going on in the statics? Well, there's the part I'm going to ignore. One is you could talk about concrete syntax endlessly, which is various forms of, like, typically there are linear representations, but these days it could involve all sorts of other things, and I'm not going to talk anything about concrete syntax. That's the point where computer science in some sense meets psychology, and I've never seen any sensible study of concrete syntax, but it feels like somebody ought to be able to do this and say something meaningful. I don't know, but at the moment it's all just a matter of opinion, and I'd rather not go there. So what we'll be interested in is what I call the abstract syntax, okay? And then the third part will be a kind of context-sensitive formation conditions. Context-sensitive conditions, okay? This is on well formation, you might say. Okay, so this is the way we're going to divide it up. Now, in fact, so I'll talk about this very quickly. So, in fact, there's room for maneuver here. For example, there's no reason why this cannot be degenerate in a certain way. And in fact, this can be more or less elaborate in a certain way. And it's never really clear, you know, what you're supposed to do. But I'll just give some example. Today I'm going to be using Gödel's T as an example because we need that for other reasons. And so that's the thing that I'll use as my little programming language. But I'll show you how this goes. So there's room for maneuver, but let's just say how we do this. So the key idea, I assume you know about abstract syntax. So the key idea, and by the way, the references for all of my lectures are my textbook, the Practical Foundations for Programming Language, 2nd edition. You can get an abridged version for free online, and I saw a couple of copies floating around anyway. You can easily find it, and so we're working from there. Everything we'll be doing will be from PFPL. Okay, so the key idea for the abstract syntax, that's what we're here, is what I call abstract binding trees, which I will summarize very briefly. This comes, or ABTs, this comes from work I did on logical frameworks, and that's the idea. And so you can think of them as having tree structure, but they also have binding and scope. So the idea is that the syntax is generated by a bunch of operators. So this is an operator. Okay, and the operators take a bunch of arguments, A1 through AN, where n is bigger than or equal to 0. That's what they look like. And what do the arguments look like? Well, the ith argument looks like a bunch of bound variables inside of a term, call it bi. Okay, like that. So this will be my setup. Okay, so this notation is meant to mean, you know, xi1 through xi, you know, ki, k sub I, where k is the number of variables that are bound within that expression. Okay, so I'll write it as x bar like that. So the example that we'll get in a moment if I do Gödel's T, so let's look at T, what would be the setup? Oh, and the other possibility I forgot is a variable x. Okay, so I wrote this down. So this is an operator and this is a variable. Those are the possibilities, okay? And so, for example, in Gödel's T, I have various operators like this. Well, I have two sorts, okay, that are going on. I have the types, which we typically write tau, so we'll write like that. And they consist of two things, an operator nat, and I'll typically use various Blackboard concrete syntax conventions, and an operator called arrow. It takes two arguments, and they bind no variables in either one, and that's all there is to it. And then there's also the expression. So T is extremely simple. So we'll write them E, and what do they look like? Well, apart from the variables, which come from the logical framework, those are for free, so let's forget the variables. We'll have the unary numerals, so we'll have successor of E, and we'll have 0. We're going to have a weird thing. If you don't know it, let me write it down, and we'll talk about it in more detail momentarily. I'll often use conventions like this. It really just means a bunch of arguments, one of which is a type, and then we have these various arguments. And I use parens and brackets according to make it look nicer, okay? But officially, it's still the same form. Here, we can think of this as a family of operators indexed by types. Okay, so for each tau, there's a recursor with tau as being its index, its parameter. And then each one of those takes 3 arguments, and it binds 2 variables in that position. So that's the idea. And then we have lambda abstraction, which if I want to follow the syntax conventions would look like that. And I have application, which would look like that. And I'm pretty sure if I didn't make a mistake, that's all the syntax. Okay? So that's a sort of an example, and you're familiar with this kind of thing, I hope. Okay? And the critical ideas are 2 critical ideas. Okay? 2 critical ideas, which I will not explain here. We can either, I hope you know them, or we can deal with them offline. So the critical ideas are one, which is because of Church is called alpha variation or alpha equivalence, okay, which is identification of the bound variable names don't matter. I'll just write it, don't matter. Okay, that's the first thing. So we identify things, whether I have x or x prime here, as long as it's used systematically, the point is the bound variable. It's just a pointer to the binding site, which is given by the dot. Okay, so we'll do that. And the second thing is substitution. And that, again, to get that exactly right takes a whole chapter in my book. And I will write it, like, for example, using E here for the case of Gödel's T. It's substitute E for X and E prime. And, you know, and the usual thing is avoiding capture and so on. So in other words, everything, you can't change, you can't confuse variables in the process of substitution. Okay, so I hope those are reasonably familiar and make sense to you. You can get the details separately if you like, but this is what we're going to need. So that's the sort of setup of ABTs. And the interesting thing is that you have to remember, in Gödel's T, no issue will come up, but I want to say this, is that I want you to remember from elementary school, the thing you learned in elementary school and that you kind of unlearned a little bit when you became a computer scientist is variables are placeholders. Okay, only. They have no other role. So the things that are called variables in almost every programming language are not variables. So these are mathematical variables, so that's an important thing. They're given meaning by substitution. They stand for an unspecified piece of syntax. So that's baked into the whole setup, okay? It's part of being civilized, okay? So this is how we get the syntax like that. Okay, so that's what I want to say about syntax, or about the abstract syntax, so we're good. Let me just check I did everything. Yeah, good. Okay, now the next thing is the context-sensitive rule. So context-sensitive formation. And these are usually given in the form of formal typing rules. I want to stress this word because it's going to come up as we go through our lectures. And I noticed yesterday on Scratch that there was a lot of confusion about this. Let me just say up front, the word formal does not mean rigorous, okay? People use it as if it's a synonym for rigorous. If you're not a native speaker, let me emphasize this. It means given by virtue of their form. It's a matter of syntax, okay? It's very important to understand this point because formal techniques, I know people use words like formal methods, like in software engineering, it's enough to make me cringe. It's like horrible because they're trying to say rigorous methods. But then why would they even say that? It's supposed to be a science, right? Why do I have to emphasize that it's rigorous? Okay, well, because it isn't rigorous, you see. So they have to use a name to convince you that what is not true is true. Okay, and then to make it worse, instead of calling it rigorous, methods, they call it formal methods. Ay, ay, ay. So it's so wrong, I can't stand it. Okay, so the point is, we'll talk about formal typing rules. So the key thing, again, I use ideas from logical frameworks here. So we have the notion of typing judgments as typical. Okay, it doesn't have to always be as simple as all this, but this is what we'll do. Okay, or you could say formation judgments if you like. Okay, they're often called typing judgments. Okay, but there is an important idea here, and I'm going to get to this. So the key things are, when does something form a type, and when is an element of a type? So element of a type, or has a type. So element and typehood. I'll call it typehood, okay? And being an element. So these are the two basic forms of judgment. So they're looking like this and looking like this. Now, in something as simple as Gödel's T, the very fact that I specify that this argument to the judgment be an ABT of sort tau, of a type, which we write tau, already answers the question. Every piece of abstract syntax of that class is already a type. So this is completely trivial. It's not the case always, but in this case it particularly is. So here I have to say something important. And so the idea is just the combinatorics. So the key idea that I want to get across, okay, the key is it's the notion of compositionality. Okay, that is what is important. Okay, And I will show how that plays out momentarily, how that comes out. But the thing that is important is the notion of compositionality. And the way this is going to play out is that what we're doing is we're summarizing some information about E, which is all and only that which is relevant to using E within another expression. Okay? That's the important guy. So if you think of these abstract syntax as some big tree, and I've got E in here, this guy up here, the only damn thing it knows is colon tau. It couldn't care less what E is, okay? That is extremely important, okay? It's really common, unfortunately it's painfully common, that people do all sorts of crazy-ass things when writing down these typing judgments or typing rules, which I'll do in a minute, that rely on knowing something more than the type because it is completely wrong-headed. It completely ruins everything. So this part of my lecture I want to get across to you is when you define a programming language, it's not sufficient to use Greek letters and horizontal lines and turnstiles, okay? You can't just like do some random garbage with Greek letters and call it a type system. I'm sorry, and people do this all the time, so I want to like really stress that. So I'll show how that goes momentarily. There's some important thing, which is a point of contact with Frank's lectures, wherever Frank may be, oh there he is, which will be a point of contact with Frank's lectures having to do with the properties of variables and the structurality. I'll show you about that in a minute. Okay, so the key thing is we want to define these things. And the important point about it being a formal type system, what I mean by formal is typing is inductively defined. By a collection of rules. Okay, and I'll say exactly what I mean by inductively defined, but the important is it's inductively defined. As an informal thing, the well-typed things are inherently going to be RE and maybe recursive. Okay, that's important. Which means that, in particular, when we get jazzier type systems in which you can interpret the elements as kind of proofs of propositions, you can only ever get a tiny pale shadow of the truth. It's not what logic is, okay? It's a way of presenting logic at the board. Okay, so I'll come back to that a little bit later. Okay, so it's inductively defined. Now, the interesting thing is that in order to define it, okay, and you can see it kind of from this picture, well, in order to define it, I need to take account of the context in which the expression occurs. So the context of occurrence. The context of occurrence matters. That is, whether something is well typed, for example, if you let me just use some informal syntax, I could define plus, I haven't done that yet. But if I write x plus x, that only makes sense under the assumption that x is a variable, it's a placeholder for a number. So it has to be of type nat. So, and the point is that the only thing that matters about the context in which something occurs, so the idea is that this being tau depends on knowing something here, and that knowing something here is nothing other than its type, okay? And that's what makes it compositional. That's what makes the whole thing work, which leads to the notion of a hypothetical judgment. So in other words, we have to make a judgment of typing in this case under hypotheses. And the hypotheses in this case govern the variables. So we write it like this, okay? And then the turnstile and E tau. So we generalize this. So we have the so-called hypothetical judgment. So this thing invariably is written notated gamma or other capital Greek letters. And we allow the possibility that n is bigger or equal to 0, and this is a punctuation mark, okay? And that's something we get from Frege. Okay, so that's the setup. So typically now what we do is we define this notion. But before I even get to what the definition is, I want to say something about what I mean by hypothetical judgment. This is the point of contact with Frank's lectures. So the notion of a hypothetical, it's not arbitrary. Okay, hypothetical judgment. It has a meaning, okay? And its meaning is given by the following sorts of properties, okay? And this is the critical thing. I am going to do what is called structural type theory, and I'm going to formulate these rules in a way that's suitable for structural type theory. Frank is going to talk about something called substructural type theory, and I'll just gesture at what that means in the most basic way, and then he'll pick it up from there. So this, just so you know where we're going. Okay, so this is the case of a structural hypothetical judgment. And I expect that the following properties hold. If I define a judgment that looks like this, it's got to satisfy these conditions. Okay, that's the important thing. So the important thing is reflexivity. Well, this one is self-evident. If you're hypothesizing something, then you ought to be able to conclude it. If I assume that X is of type tau, then it's of type tau. I mean, that's it. You have to have this. But it's called reflexivity because it's sort of like, think of this as a binary relation. It's reflexive in the sense that this is related to itself. Okay? All right, so that's how that goes. So that's reflexivity. The other thing, these are completely indefeasible. These things cannot ever be denied, okay? Well, otherwise you've got garbage, okay? So that's important. So what is a transitivity? Okay, so the transitivity, I'm going to formulate it in a way that's convenient for me. In a substructural setting, you need to be a little more careful, but I'll leave that out of here. Okay, so what I want to say is the following thing. Variables are placeholders. So if the formation of this expression relies on some slot being of type tau, and you actually have something of type tau in the same ambient context, that's where the substructurality gets more delicate, but let's not worry. Okay, and I'll write it like this. I don't want to use a horizontal line because horizontal lines confuse people. Okay, so I'll say if then, okay. Okay, let me write it like that. If this is the case and that's the case, then it has to be the case that this is also true. This is specialized to the setting of typing judgments and so on. This is really something more basic and generic, but I'll do it in this context, okay? These two things are absolutely indefeasible, okay? If you don't have this, you don't have a consequence relation. The turnstile is denoting what is called a consequence relation. You don't have a consequence relation, and you're just talking junk. You're just talking garbage. It doesn't make any sense, okay? Or another way of saying it is, you have no business using this kind of notation if you don't have this, if you don't have these properties. It would be like using equal sign to mean, less than. I mean, it was like, why are you writing it as equal sign, okay? So don't write it in a way if it doesn't have these properties. Okay, now the ones that are defeasible are called weakening, which says this: extra hypotheses don't matter. Now you might think, God, what could, let me put that there. What could be possibly more self-evident? Well, this is deniable. Okay, so I'll just write star here. All of these things are deniable, but for my purposes, it's like this. In an ordinary situation that you're familiar with, when I type something, all I care about is what the assumptions are on the variables that are here. If I take a variable that isn't there because it's not already in gamma, then I can throw that in and ignore it, okay? That's called weakening, and it seems self-evident, but Frank will show you the incredible beauty that arises from denying that and two other principles. Okay, so that's the whole enchilada here. That's the idea. Okay, so that was number 3. Yeah. So number 4 is called contraction. And it's easiest if I just write it out in the simplest possible form. There are different ways I can write this out, but the idea is I can do it like this. If you can get something here, okay, tau prime, let me write it like this. Then I'll write it. There are different ways of writing it. Which is, if I have two different variables of the same type, I can identify them. Did I do it right?
Yes.
Okay. Oh, okay, sorry. What's the question?
In weakening?
Yeah.
Then?
Yeah, X is not all the way around. Is that what you're asking?
Yeah, the and. The and.
And, then. Then, okay, good. All right. All right, so this is contraction. This again seems like totally self-evident that you don't really care. If I have two variables of the same type, I can just use one, okay, if I want to, okay, that this is totally valid. And you might think, again, how can that possibly matter? Well, that's another subject, okay? And the other one I'll call exchange. And I'll just write this, it's easier if I just say the order of hypotheses doesn't matter. Okay, I can swap them. So if you want to really write it out, if you have something which is x tau, y tau, I'll just put it, you can put it in the middle, you can put it at the end. Let's do it like this. E prime tau prime, then it's also the case, I'm sorry, I should have called that tau 1 and tau 2, let's say. Then I can put them in the opposite order. So therefore, let's call x1 and x2 just to make it look nicer. Okay, so let's do x2, x1, tau 1. And again, this seems like utterly self-evident. Why would you even matter? Why would you even question that? But I'll put the stars in there because they're defeasible, okay? So the important point is if you write down something using the kind of turnstiles in Greek letters like this, it had better satisfy these properties. And in all likelihood, unless you really know what you're doing, one or more of these may also be in play, okay? So for the purposes, my purposes of structural things, structural means all 5 properties have to hold. That's just the words we use, okay? So that's important. Now, you would think, okay, so that's the point I want to make. Many times in papers I see, in various forums, people write down type systems that have nothing like these properties. They're just complete garbage, okay? And I'll show you something that people do that is completely illegal, and I'll show you that in a minute, okay? All right, so good. So now let's do an example. You've seen this kind of example before, but you see I wanted to put it all in context. So what I will do is I will define T is static, okay, the following way. So here's what I'm going to do. Here's the important thing. I'm making an inductive definition. When I make an inductive definition, I'm defining this 1, 2, 3 place relation by a collection of rules. So I'm going to say it's the strongest or the least or the strongest relation. I'll write it like this. Really, if I wanted to be careful, it's the strongest relation R gamma E tau closed under the following rules. This is the strongest one closed under the following rules, but it's conventional, okay, closed under, which is, you could say, obeying the following rules. Okay, it's important that you understand that that's what is being said, okay? That's what matters. So the strongest is very important because it means you have what is called a universal property. Okay, universal property, for my purpose, whenever you see an EST, okay? So when I talk about the least upper bound, the least of all the upper bounds, or the greatest lower bound, the greatest of all the lower bounds, it's an extremal clause. And its extremality is where the whole point of it is, okay? So that's important. And one form of jargon of this is it's a universal condition, okay? Now, you have to, if you really want to be rigorous, which I'm not going to do at this moment, you could ask yourself, well, why is there a strongest one? Well, that's a story. So I'll appeal to something called Tarski's theorem, and I'm just not going to talk about it, okay? So there is a strongest one, okay? You have to be careful, you know, just because you talk about the strongest thing such that, it doesn't mean it exists, okay? But in fact, it exists. Okay, so that's what we'll do. So we're going to write it down in the following way. The typical format is it looks like this. What am I doing here? I'm ensuring that reflexivity holds because I could take gamma to be empty. So I'm ensuring that reflexivity holds. And there's nothing above the line. So it's important that I write it the way I write it. Okay. I write that 0, I can put the parenthesis if I want, is nat. And I write if E is nat, then nat. Okay, good. So these have the form of what are called axioms. The rules have no premises. This is a proper rule that has a premise. Then there's a rule which gets tiresome to write down, but you have to get used to it, which is the recursor, which says if tau is a type and E is a nat and E0 is a tau, and with X being a nat, this is the way I did it in my notes, there are variations here. That's a tau. than the recursor. I'm going to assume from the lectures that Paul gave and your reading that you more or less know what this is. I'll explain it. I can write it like that. Okay, I'll explain it when I give the dynamics. Okay, but that's just the typing rule. So it has 4 premises as written out here. So there are 4 premises, and then there's the expectable rules about lambda. So I have lambda abstraction. This is a tau arrow. Let's call it tau prime. If I make the additional assumption tau, E is tau prime, and tau is a type. Okay, the tau is a type part. I'm being a little finicky because, as I said, it's trivial. It's just the syntax. The very fact that I can write it down makes it a type. But let's just do it just to be official about it. Okay, so I'll write it down like that. And that's it. That's the statics. They're all done. Oh, application. I forgot to. And what?
Why tau?
Yeah, y should be tau. Yep, thanks. Good, thank you. And I forgot application. So if I can have, you know this, but let's write it down. And then I can have the application. Apply E1, E2 is tau, written like that. Okay, good. And those are the rules. That defines it. So the idea is it's the strongest relation, okay? So that is gamma turnstile E tau holds if and only if it can be derived by the rules. I'll just write it like that, according to the rules. So there's 2 directions to this. This way, you can build up a derivation tree. I assume you know how to do this. I don't have time to go into it. I can just start composing the rules and putting them together and arrive at something that is of interest, okay? The other way is the interesting thing because it's the principle of rule induction. Okay, so the idea is that I have a reasoning toward this judgment. You just use the rules and build them up. I have a reasoning away from that judgment. That is, if I know this is the case, what can I do? I go by rule induction, okay? And the idea is that it must have been established by a composition of rules. And so I just look at all the ways. I'll come up with an example of this in a minute. I'll look at all of the ways in which that could have arisen for the particular E and tau and gamma that you have under consideration. And I look at all the ways it could have arisen, and then I prove some fact from it. So this is reasoning from, and this is reasoning toward. So with inductive definitions, they have what we call a mapping out property. The universal condition has a mapping out property. You can go from here to other stuff, okay, so what is the idea? Is a way to say it is, we can say that this implies some relation, some property of gamma E tau, okay, if, okay, for every, R is closed under the rules. Is closed under or obeys the rules. Or obeys the rules. Okay, that's the idea. So, for example, that's the whole idea. R is the thing you want to show, and you want to show it from the fact that something is well typed. Well, the data involved in that being well typed is gamma E and tau, so I want to show some property of gamma E and tau. You'll be able to show this regardless. This is really for all gamma E tau, if you want to be precise. Then I can show this by just going through every single rule and showing that it has the property R. So let's give an example, okay? Let's look at weakening, okay? I want to show that if this is derivable, then so is this, okay? Why should that be the case? Well, here's the slick way to do it. All right, you can write it all out, and it's fine and pleasant, but here's the idea. I'll put it on the left for my convenience because the order doesn't matter, okay? And I'll call the variable y colon sigma just to get it out of the way, okay? Well, this rule is stated for an arbitrary gamma, so let me put y sigma here, and now reparenthesize and call that the gamma, and then I've got an instance of the rule. And so it's derivable. I can throw a y in there. Here is the same. I can throw y sigma in here because that's my gamma, and the rule is schematic in the gamma. Here, by induction, I know I can do this for whatever reason, and therefore I can carry it down because the rule just carries down the gamma. So I can just do that. Here is the same. I'll put y sigma here by induction, y sigma here by induction, y sigma here by induction. The rule could care less. It just carries down gamma, so redefine what gamma is, and you get that. Okay, you're done. The same holds here. Put y sigma around. We have to be careful because identifying this thing up to alpha conversion means that whatever x is, it's not what you think it is, right? It immediately, as soon as you think it's maybe y, it immediately becomes something different. It dodges, it gets out of the way. That's the beauty of taking this modulo alpha. So this x and that y will never be the same, okay? Because this is a bound variable. That's a nice thing you use all the time. And therefore I can put y sigma here. And similarly, I can put y sigma here, reparenthesize, and I get y sigma here. And now I've proved weakening. Okay, that's it. So this thing has weakening. For example, one moment. Suppose I had stated the variable rule as just this. X colon tau gives me x colon tau. Then I wouldn't have weakening. Because the rule, if the rule were literally that, for any choice of x, but only one, as soon as you put in 2, the rule doesn't apply, and now you're screwed. Okay? So I phrase the rules to make this come out true. That's the reason why people put all the gammas there. It's not just a matter of like some, cargo cult of putting up the wooden radar thing to call in the gods of supplies, okay? No, it's not a cargo cult. There's a reason for everything, okay? And 90% of the people out there know this, I can tell you, okay? So you will know this, okay? So that's the idea. Now there was a question somewhere, I lost track of it. Yeah. Could someone relay that?
What's the implication? The gamma, the superset implication?
Here?
And like he's asking, so when you go from gamma e tau to r gamma e tau, he's asking what's the meaning of the implication?
Oh, implication, math. If then.
Object or meta?
Yeah, implies.
So meta language.
I write horseshoe. That's my way of writing implies. Okay. Good. Make sense? See, it's easy if you do it right, but it's very easy to do it wrong. Okay, now let me give you another example of something you cannot do. You cannot write on this rule, provided that in the whole program, no other lambda occurs. Oh, you may think it's designed to be sort of comical because it's like an absurd condition. Okay, but I can pull out papers left and right out of, Oops Law and places like that. I can pull out rules that look like this. They're garbage, they don't mean a thing. Okay? The entire point about these typing rules, they're local. Everything that this guy knows about the context it's in is given right here. You can't then put some random English over here to say that and then the whole thing makes sense. Whatever you're doing when you're doing that, you're not doing typing rules. You're not doing a programming language set up in the way I'm describing. Okay, and therefore you shouldn't be using Greek letters and horizontal lines if that's what you're going to do. Okay, so a lot of times people will do things like various forms of program analysis, and they'll try to write them out with rules, and it's just invariably a mess. Okay, and it leads to lots of confusion. So let me not catch you writing anything like that on your rules. Okay, so that's the thing I want to stress here. Okay, so good. All right, so that's the setup there for the statics. Now let me check where I am in my notes. So that's what the thing looks like. So what I'm trying to convey to you is the inside game of what's really going on there. Okay, so let me make sure I've got all this thing. Okay, rule induction, good. All right, now I want to talk about the dynamics. Okay, any questions so far? Yes?
So is it fair to say that the turnstile relation is a relation on a set of lists of typing judgments?
Yeah, the way I'm doing
Typing
well, it's a hypothesis list, which in my case, I'm simplifying a little bit here, but my case, the hypotheses are always variable colon type. So that's the gamma is a bunch of those. If I wanted to be really accurate, I'm not going to do it. I'll talk to you offline. There's a slightly fuller story here, but this is good enough. Yep.
And I'm being dumb here, but is the strongest relation the largest or the smallest?
Smallest.
Smallest.
Yeah, strongest in the sense of implication. A is stronger than B if A implies B. Yeah, and weaker the other way around. So, yep. So it's the strongest relation. Yep. Okay, make sense? Good.
Another question.
Yeah. Up.
Regarding awakening, instead of have awakening everywhere, is it possible to have awakening only on the right or on the left?
Well, there's no notion of weakening on the right. The way I've set it up is I have hypothetical judgments have, I might have erased it or it's obscured, have a certain form, and it pertains to the context. Weakening of the context. I'm not saying other things can't be done. It's just like, this is what I'm doing, okay?
Using the exchange rule, I will be putting restrictions on expressibility of your P form.
Could someone repeat that question?
Just having exchange,
Yeah.
put restrictions on the expressibility of the language.
Well, yes, because as soon as you deny these properties, you can now make fine distinctions, like whether one variable is declared within the scope of another one. Okay, if I have exchange, you can't tell. They could have been declared in any order. Maybe you care. Maybe you care that there's some kind of stack thing going on here by which I declare X and I declare Y inside of it, and I don't want to lose track that Y was declared inside of X. That's a meaningful thing that one can do, okay? And then you would deny exchange. The only thing to repeat myself, these are not deniable. Okay, that's the important thing. So it's really, in some sense, it's a pre-order. Okay, it has to be a pre-order. Okay, good. All right, so let me move on. So now what I'm going to do is talk about the dynamics, and I want to, again, give you a little bit of the inside game about dynamics. Okay, so let's do this. So I'm going to set this up in a fairly general way and then specialize it. Okay, so dynamics. So what is the idea? How to execute things. Things become programs. By the way, there's nothing that requires me to have the statics be given by a typing judgment. That's just illustrative. I could decide, for example, that an expression is well formed if it has if all the free variables are declared. Okay? That's it. I could just say everything is okay, all right, and provided that you don't have any dangling variables. Okay? That would be a definition of a statics. But nothing wrong with that as far as a definition of a statics is concerned. I'll have something to say about that later because it's related to some issue called dynamic typing, which I'll come back to later. Okay, so we'll get to that. Okay, so good. Now what is the dynamics, which is how to execute things? Okay, in fact, what does execution mean? So the way I'm going to do this, you have to specify the following data. You have to say, what are the states? The states of execution. Let's call them S. You have to specify state transition, what it means for one state to evolve into another, and you have to say what is an initial state, and you have to say what is a final state. And this is how you know you're done. So this is when you're done, this is how you start, this is how you continue, and that's the setup. So it's an abstract machine. However, the word abstract machine, I'll call this a transition system, is often freighted with additional meaning that I'm not giving it here, okay? So this data constitutes an abstract machine, that's it. Okay, that's what I want to do. Okay, so in the case of T, I'm going to give it a dynamics. And by the way, Gödel did not give it a dynamics. Okay, this is something that we're doing in addition. That's going to raise some issues coming up because I'll come back to that a little bit later, okay? So I'm going to endow it with a dynamics. Okay, that's what is important. T, unlike F, this came up last night in an oblique way on the Scratch, actually is a programming language, okay? Whereas F, for example, is not. And I will explain that a little bit later. Okay, so let's look at T. So my idea is going to be this. What are the states? I'm going to decide like this, is it's closed expressions of type NAT. The idea is that NATs are observable. Meaning I can just tell the difference between 0 and successor. Okay, so I can observe the outcome. I can see it finitely. If I didn't specify that it be nat, if it was a function, you're going to have some trouble with function extensionality, that is, functions being defined as sets of ordered pairs or defined by their I/O behavior. You won't be able to tell what the answer is. Okay, so that's not what we want. So we're going to say we have a notion of an observable. The problem with F is it has no notion of observable. And so you have to equip it with one in order to make it into a programming language. This starts to, it's an indication of why the vaunted Curry-Howard isomorphism, as it's called, I don't use that phrase, it breaks down. It doesn't actually work for programming languages. That's a myth. Okay, so I'll explain that a little bit later. Okay, ENet, okay, is that. So what am I going to do? Let's say, what is initial? So we'll say E is initial. I'll just say always. Okay, any closed expression of type nat can be executed. Okay, because the states are all such things. When is E final? I'll define it when E is a value, which I'm going to define. And then I will define transition, which I'm going to define. Okay, so this is evaluation. So the point is that execution here is evaluation because it's a functional language. The states don't have any other fancy thing going on. It's just a matter of simplification or evaluating expressions. It's sort of like how you got into this business to begin with. Way back when you were in elementary school, you've learned the elements of algebra, and I'm absolutely certain you just loved messing about with polynomials and simplifying them and factoring them and stuff because you were a born computer scientist. That was like, this is it. So what we're doing is we're talking about those simplification steps, okay? So that's what we're going to do, make that in a particular way. So that's the idea. And these are going to be inductively defined. And I'm going to use Plotkin's method of structural, oh, there's that word, structural operational semantics. This is the way to go, okay? So it's SOS. All right, so we're using structural operational semantics. There is something else called SSOS, substructural, but let's not go there. I'll just leave that for Frank if I don't actually know what he's going to do, but he might. Okay, so that's called SOS. SOS is like perfect for these ideas, okay? So it's given by, it's inductively defined. So there's a bunch of rules that tell you what it is, okay? So now I'm going to do that. And this makes everything work out extremely smoothly. There are other methods of specifying state transition systems. You can do whatever you like, but I'm telling you, do it this way, okay? This works. My whole book is based on SOS. I view my whole book as just an amplification of what I learned from Plotkin 30 years ago. Okay, that's like basically what I look at it, the way I think about it. Okay, good. So let's see how this is. So now there are choices. And I'm going to make two important choices. I'm going to distinguish eager and lazy, and I'm going to distinguish call by value and call by name. Nobody knows why it's called call by name. It doesn't mean anything. I don't even have a guess. I don't know why it's called that. Okay. All right. Okay, so this is what we want to do here. So let's specify the values. Well, regardless of what you're doing, 0 is a value. Okay, that's a fully evaluated expression. Now the question is, I have a choice here about successor. Okay, and I'll put it in brackets up here. E is a value, and this indicates what we do if it's eager. I'll write brackets eager here. If you want to specify an eager evaluation strategy, eager pertains to the constructors, to the value constructors. So 0 and successor. So for this to be a value, E has to be a value. In the eager interpretation, in the lazy interpretation, not. In a language like T, who gives a damn? It doesn't make any difference. Do whatever you want, okay? But as soon as we get to PCF, it makes all the difference in the world, and you can do it wrong. And there's a right answer, and there's a wrong answer. And the wrong answer is lazy. So we'll get back to that in a minute, okay? For Gödel's T, no problem, okay? Either way, it's a choice, so I'll just present it that way. Okay, so that's important there. Now I can specify what other things are values, which is not, the eager lazy doesn't enter into it, which is that it's a functional language, so functions are themselves values, independently of anything about the body, okay? So those are values, and those are all of my values in Gödel's T. And now I have to specify evaluation. So how do I specify evaluation? Well, for application, I'll start here. We can write a rule like this, and here is why it's called structural operational semantics. I use the structural abstract syntax, the ABTs, to define this transition relation by a collection of rules. That's what's important. Okay, so if E1 steps to E1 prime, then the application steps. So it says, look, in order to evaluate an application, you have to figure out what you're going to apply. Then the call by value, call by name distinction comes up, which is that suppose I have a lambda here. I can write it like this. And then I'm looking at E2. And now I have a choice, okay? So for call by name, you just plug this in. And for call by value, you know you actually need another rule, which says that if E2 transitions to E2 prime and E1 is a value, so if you figured out what the function is, you now have to figure out what the argument is. That should have said that. And then you have call by value, which is beta value rule, and this is called beta, and then you say this. If E2 is a value only, then I plug in E2 for XE. Okay, good. So that's those rules. So that's how we do this. We have a choice here what we're going to do. So it's kind of this or that. Okay. Now, you might wonder, why do I specify a left to right evaluation order here? I don't have to. I can specify that they work in parallel. That's the basis of parallelism arising from eager functional programming, okay? You're screwed if you have lazy, forget it, non-starter, okay? But in the eager case, we can do parallelism. It's great. The future of parallel programming, it's all based on eager call by value functional programming, okay? I don't have time to talk about that, okay? Any further. It's in my book, look in the book, okay. So, all right, good. Some years I have, but anyway, so that's that. And now I have this horrible rule. It's very hard to write down, I'm sorry. How about if I introduce some notation? So, because it gets so awful, okay? So let's write R to be, I'm sorry it's so awful, but there is no getting around it. All right, let's write R for that guy. Now you see why I used the funny parenthesization. I was anticipating this. Okay, so now what do? If we want to evaluate R of E, in other words, I want to recur on a number, I have to know what number I'm recurring on. Okay, so just plug that guy in there and you'll get the right thing. I'm abusing notation a little bit, but believe me, it's better. Okay, so we do that. And now you have to decide what happens when you have R of 0. Well, that becomes E0. That's the base case. I know from the weekend that you've already done this, so I'm not going to dwell on it at all. And if I take R of successor of E, well, now it depends. We're going to insist that successor of E be a value. Notice that the premise is that, because maybe it's a value regardless of what E is. Maybe it's only a value because E is. Anyway, that's handled over there. So I demand that this be a value, okay? If that's a value, then what I do is the transition is you plug in the predecessor plus the recursive call on the predecessor for X and Y in E1. And those are all the rules, okay? That's it. So that notation helps us a lot. Okay, and that specifies the dynamics. And now we can rattle off a few things straight away that are useful, okay? So one is, I had a specific terminology and order that I worked out to my pleasure last night, so let me figure out how I do this. Okay, yeah, so first of all, very easy fact. So 1, if E is a value, then there does not exist an E prime such that transition. So in other words, values are, you could say stuck, are stuck. I don't know if you want to say that, or finished, or whatever you'd like to say. Okay, they're going to be final. Okay, That's the idea, okay? So a value is not susceptible to further evaluation. Second thing I might like to say is that for every E, there exists at most one, I'll call it V, such that V is a value and E evaluates in multiple steps to V. Now, what is this relation? Let me save you a lot of heartache. Define the relation in the following way. E arrow star E. If E goes to E prime and E goes in star to E double prime, then E goes in star to E double prime. This is my definition. It's going to help you a lot because I'm going to ask you to do this for homework. Okay, and I'll ask you to figure out how to do this. Okay, and there's another one that comes up where this becomes very important. Okay, so this could be called determinism, if you want, or it's what makes it a functional language. It says that the evaluation relation is a partial function. Okay, that if I have the relation, or the multi-step evaluation relation, what I'm saying is the multi-step evaluation is a partial function. Okay, that's what makes it a functional language. It has a precise definition. It's got nothing to do with any other ooga booga, okay, which are very, very, very hard to define what they mean. What do you mean by a functional language? Because after all, you know, ML has mutation and IO and all sorts of things. And Haskell is a dialect of Algol, which was one of the original imperative programming languages. So what the hell are we talking about? Okay, well, it's all woolly, messy stuff. Let's just look at it this way. The evaluation, multi-step evaluation to a value is a partial function. Boom, that's it. That has a definition. Yes?
I may have missed what you said this, but what is the purpose of saying that the states require E to be in that before allowing a function to be a final value? I thought when you said the states requiring E to be in that meant that like we were...
The states are required to be numbers, I said, yes. Could you rephrase the question? I didn't catch it, sorry.
I guess I don't understand what the utility of saying that is if we're not requiring that our computations end with a natural number.
Not requiring.
We're allowing programs that evaluate to a function because we've said that functions can be valued.
Oh, that's true. I'm just saying the outcomes are going to be natural numbers. That's the thing. Yeah, I made a mistake. I just realized as I said it, because of the structural operational semantics. Let me get back to the observables later. Let's just put any type tau here. When I wrote my notes last night, I wasn't thinking of something. Let's leave this alone. I'll get to the observables later and what the role of that is after all. Okay, because I just realized that I made a mistake because I'm evaluating here, and that would be a functional type. So that's, I want to be careful about that. So I'll get to that in a minute. Okay. All right, good. So that's like some setup of what we do. So now we've defined the operational semantics. Okay, so that's how we do it, and good. And that's how we can say we have a purely functional language. Now I have to do a sanity check, which is the coherence. Okay, so let me do it over here. The coherence is you could actually wonder, does all this actually make sense? Because I'm writing down these relations, and now here's the thing to notice, and this is going to come up later when I give a deeper critique about type theory in programming languages. Notice the dynamics, I don't know what the way to write it is, doesn't care about types. It's defined on the raw syntax, on the abstract syntax. There's a reason for this, okay? And it's the thin edge of a wedge. It's part of what tells you that some standard story doesn't really work, okay? So I'll get to that a little bit later, okay? So it doesn't care about types. It's defined without regard to types. But I can prove that it coheres with the statics, okay? Of the dynamics with statics, which is called safety, okay? And it can be stated in the following. I have a state which is well-formed, and I do take, which is defined without regard to that fact, then the resulting state is well formed. So this is called preservation. But what it's doing is it's telling you the coherence, okay, of the statics and the dynamics. And the second thing is, if a state is well formed, then either it's a value or there exists an E prime necessarily one such that E steps to E prime. And this is called progress. And I want you to notice that this makes a pas de deux, okay, that I want you to see. Because what happens is you go along, you take E colon tau, you make a transition going here to E prime colon tau. That's well formed, therefore I can make a transition. The two things sort of work together like this, okay? If I have a well-formed thing, I take a step, it's well-formed. If it's well-formed, then it's either done or I can take a step. If I take that step, it's going to again be well-formed, and so forth. This is how they fit together, okay? So this is what the whole idea is, okay? And again, I know that you've done some of this in prep, and it's in the book. Do this for homework. This you go by induction on transition. I've seen 80-page papers doing the most unbelievably preposterous things because they do this proof on the wrong thing. They try to do it by induction on typing, and it's a mess, okay? You want to do it by induction on transition. Here, you don't really have any choice. Mapping out from E colon tau, what else do you have to work with? You use the mapping out property, so you go by induction on this. Here, you have two things to work with. That's the guy, okay? So if you do that, everything is completely simple, okay? So that's how that works. Okay, so I'm not going to go through the proofs of the board. We can do that this afternoon, or you can do it for homework, okay? And now what Dan is going to do this afternoon, I'm jealous, but it's one of the nicest theorems there is that for every E which is well typed, notice this doesn't guarantee termination. There exists a unique V which is well typed, and it's a value, and E transitions to it. Unique, okay? And this afternoon, Dan is going to do this. And it's one of the most beautiful results in the world. It was Bill Tate, who was a very influential type theorist, logician, mathematician from the University of Chicago, no doubt retired now. And you'll learn about Tate's method. Tate's method is one of the cornerstones of the whole field. Okay, so this is something you'll do. Okay, so oh good, I even have time. I have some bonus stuff here, so I have some time. Okay, so before I do the bonus stuff, let me pause and give you a chance to ask questions. If any, yes.
Is number 3 of that, isn't it just the same thing as number 2 the whole way?
No, because this says at most 1. I use some funny notation. There exists less than or equal to 1, okay? So it's a partial function. So this says it's a partial function. So this is a partial function. And what Dan will show you is it's a total function. And, you know, it was an open problem for a long time because it implies the consistency of arithmetic. See, and so this is that's the important thing. Gödel showed that you can reduce the consistency of arithmetic to the fact that this is a total functional programming language, basically. And then Tate showed that it's a total functional programming language. And so arithmetic was consistent. So if you know anything about formal logic, you know that if you have a way of proving that arithmetic is consistent, there's something non-arithmetical going on in your reasoning, okay? And that's true, and that's the, what should I say? That's the tragedy, if you will, of formal systems. You can never, ever validate the formal system because to validate it requires methods that are more powerful than the ones you're doubting. So go for it, but it's an endless thing. Formalism doesn't work, okay? So that's my position on these things, and we'll talk about more about that when we get to more advanced type theories. Yes.
For the R that you made like somewhat equivalent to that expression, you pass it a parameter, but I don't understand which parameter it is in the expression. You have like R of E, but there's no.
Oh, yeah, because I'm abusing notation. When RV means do that, and then that is notation for it's really the third argument. Give me that, otherwise I'd be writing out those recs over and over. You know, it's dreadful. Okay, it's dreadful to write and it's dreadful to read because you have to pattern match it. Is it really the same rec or not? Oh, okay. So give me that. Okay. Good. All right. Good. So then I want to just do one little bonus thing. Go ahead.
One more question. So about the distinction between eager and lazy. This distinction is for the value, the value.
It's for the value constructors, yes. Eager and lazy pertains to the value constructors.
Okay.
And then call by name and call by value is a separate issue. That's got nothing to do with eager and lazy, in my opinion.
Okay.
Okay? So that's...
And then when we talk about lazy evaluation, like
Well, people speak loosely then, okay? And then they combine the two and call them one. But then they try to undo it by having special exclamation points and stuff like this to undo the conflation of the two notions. I feel it's better to do what I did. Okay. Yeah, I have a tendency to say things my way.
And then, so what's so wrong about lazy
What?
data types?
What's that again?
What's wrong with lazy?
We'll get there when we get to PCF. Okay. Paucity. The answer is a paucity of types. It's grossly inexpressive. That's the answer. You're screwed. It's like you're so screwed, and so and there's no recovery. Okay. And notice I'm also using the words carefully. This business about being functional, being the evaluation relation is a partial function. I care about that. Okay. So, all right. But yes, it's the way I am. I have my own way, my own vocabulary and stuff. So I try to explain at least how it relates to other things. Okay, so let me do a little bonus thing because it comes up sometimes. Oh, yeah, sorry.
This sentence about the functional language in the partial, smooth set relation function in the partial function that defines the functional language, correct?
Is that what? Sorry.
So, what's the difference in an imperative function? Can you define?
Yeah, that's the thing. These things are not extreme. My point is that you could also, deterministic. If I'm going to use an adjective, I should have called it deterministic. You could also just use the word deterministic. I'm using the word functional because the relation is a partial function.
So you can define that on an imperative language?
Yes, it's also, yes. Because you see, the so-called functional languages are all imperative. I can print hello with ML. I can print hello in Haskell. What are these people talking about? Okay. Yes? So there's a history about how things came about. And people need slogans. They need flags to rally behind. But at the end of the day, when the smoke clears, what we're talking about is sensible, civilized, mathematically well-structured programming language or not. Okay? All right, that's the thing that I care about. In fact, yeah, okay. Okay, so, all right, so here, let me do a little bonus thing. So here's a little bonus, it's sort of fun. It's also pretty common to define an evaluation relation, which says that E evaluates to B. And this is handy for a lot of reasons, but it's not good for doing meta theory. So when we defined standard ML 30 years ago, we used this kind of thing, and it was cool and seemed like the thing to do, but I totally regret it. When I redefined standard ML, I used SOS. Okay? And then we did a complete mechanization of the safety of the entire programming language, absolutely done, all in 12, machine check proof, the only programming language at scale that it's ever been done for. Okay? So, and the crucial part of it is using SOS. But one can define this relation because it's handy. It's really handy for like the user manual. Okay? So it's good for that. It's just not so good for doing meta theory. So how do we define it? It's inductively defined, oddly enough. Okay? We say if Z is a value, then it evaluates to itself, okay? Where I defined value as before. And then I write out these very natural looking rules. For example, if I have application, I can say that evaluates to V if E1 evaluates to lambda xe, and I'll put in brackets because it depends on whether you're doing call by value or not. Let's call that V2. Okay, so I'll put that in brackets. And then you continue by plugging that in and evaluating the body and getting V. Okay, so it's written like that. So that's a rule for doing that. And then, oh, I don't know, let me just write similarly for the recursor. All right, let me not write that out, it's a little tedious, okay? So that's enough to give you the flavor, I hope. I think that's right, yes, because I've covered things here. Well, this is a little bit facile, okay? What I really should be doing is this. I could say 0 evaluates to 0, and then according to whether you're eager or lazy, you can evaluate the argument and then decide what the successor evaluates to, and then the choices are itself or successor of V. And then you need one more rule that says lambdas evaluate to themselves. Okay, that's really what I want to do. You write them all out like that. Good. And now you can prove the following fact. So first of all, this is what the fact is, okay? It's a partial function. That is, it's a binary relation that has the uniqueness property, that for every e, there's at most one v, okay, to which it evaluates. Good, all right? But there's no idea of progress. There's no way to sort of say that if I write down an e, like that some rule applies or something. You have to have some way of saying that you can do something, okay? That's not very easy. But what I can do is I can prove the following fact. This is the easy part. If E evaluates to V, then E multi-steps to V. Okay, and here we do this by rule induction. It's a mapping out property. This relation is inductively defined by the rules that I sketched here. So you go through all of those rules and you derive for each premise this multi-step, and then you do some pasting. So you do some sort of pasting. You'll have to see what I mean. When you write it down, you'll see what I mean, okay? This is not too difficult. This is a little challenge. If you've been paying absolutely careful attention to what I've told you, it's easy. If you have been like, saying, yeah, you're going to get stuck doing this. So, which is, how do you prove the following thing? You see, there's a problem that then E evaluates to V. I want to prove the converse. Notice where V is a value. I read V, but I want to indicate V is a value, okay? You see, there's no way to say, if I look at every transition like this, what would I say over here? Because the right-hand side has to be a value. How am I going to relate it? It's not so obvious what you do. And if you start thinking like they taught you in school that this is, any number of steps and bring numbers into the picture, you're just going to make yourself suffer, okay? So pay attention to what I told you and prove this, okay? So this is homework, okay? And be enlightened. You will discover some very novel, interesting idea that I'll bring up a little bit later. Okay, I'll mention a little bit later, but I want you to discover it. So I actually told you how to prove this, but you weren't paying attention, I think. So that's that you want to prove there. So this is the thing that tells you, okay, what is the relationship between this evaluation relation and the transition relation? And then from this, I can get some kind of type safety theorem, because if I want to know something about this being well typed, and I want to say something about not getting stuck, that you don't get into some ill-defined state, well, the way you do it is you turn it back into a transition system, and then you have already proved the requisite properties of transition, and then you're good, okay? So that's very important. So that's like, this is a thing one does, but in my mind, the evaluation relation is sort of secondary. The transition is what matters. And there are various ways to argue that. One I offered earlier has to do with metatheoretic convenience and so on, but another is that the very nature of computation is that I'm here, I know how to take a step. It goes back to Turing's model. I'm sitting at my desk, I have a pad of paper and I have a pencil. I write something on the paper and turn it over and take another fresh piece of paper and write on it, and I can look on either side of what I've just written. Okay? In other words, it's extremely clear what is available to you to take the next step. Okay? That's the very definition of computation. So to me, the transition system is fundamental in this regard. Okay? You have to have a transition system. However, I fully grant that when it comes to writing the reference manual, this is a perfectly, a very nice way to write things. Okay? But when you're interested in all the foundational issues, as we very quickly will be when we get more advanced type systems, it's important to get some of those basic ideas right. Okay, good. So that's enough for me this morning. My throat is dry. We can take further questions this afternoon. If there's any quick questions, I'm happy to answer them. And otherwise, we'll take more involved questions this afternoon. And Frank will be next. I think that's all I have to say. We got a quick break. Okay, thanks.